Okay, so this video is meant to introduce you to the idea of oscillations or periodic movement. And so there is a key difference between just periodic movement versus something called simple harmonic motion, which is a very specialized case of periodic movement. So periodic motion is when you have repetitive motion. So there is a definitive pattern to the motion. There is like a constant angular velocity or rotation. So something spinning on a turntable is periodic motion, like it happens continuously at a consistent rate. Now, simple harmonic motion is repetitive motion, where, so here's the caveat, where the restoring force that's causing the motion is proportional to the displacement of the movement. Okay, so this is repetitive motion where the restoring force that is causing the motion is proportional to, it's actually to the negative of the displacement. Okay. So two classic cases of simple harmonic motion are springs, simple spring systems, and simple pendulum systems. So if I think about like my spring system, if I have a spring and I got a mass on there, and let's say that this is my equilibrium position, and I were to stretch it out to here, so my spring got stretched a distance x, there is a definitive force acting on my spring. That's the spring force. And the spring force is proportional to negative kx. So it's proportional to the displacement. It's actually proportional to the negative of the displacement because it's a restoring force. It's causing it to go in the other direction as the displacement of it. Okay? And another case is a pendulum. And so in this case, it's moving a particular angle theta, and there is this component of gravity that is like pulling it down. It's actually, I totally could have drawn that better. Where's my eraser? All right, guys. It's easier to see the component of gravity if I were to draw my weight vector. I have tension. I have this, what I'll call WY, that is opposing my tension. And then I have this WX, and it's this WX that is opposing this angle. Okay? So again, we have two cases where the restoring force is proportional to the distance or the displacement, but it is negative. Okay? So this is simple harmonic motion, and to kind of remind ourselves of the quantities or ideas with periodic motion. So this is a little bit of review from when we talked about circular motion, quantities of period, frequency, and now we have this other quantity called amplitude, and I may have referred to this before, but let's just define them all again for this unit. So the period is the time for one cycle. Golly. In periodic motion. Recall that our symbol for it is a capital T. The units for it are seconds. So wobbly board. Frequency is just the inverse. So frequency is the number of cycles per second. It is actually represented as an F, and you could calculate it by saying it's 1 over the period. And the units are 1 over seconds, which is a hertz. We abbreviate that as Hz. There's something else called angular frequency, and I don't have room for it on my board, but I'm going to write it here. I do expect you to write it down. Golly, frequency. And we can think of this as just like there's angular velocity, right? Angular velocity is our change in theta over change in time, right? Well, if I think about one rotation, okay, for one rotation, my change in theta is 2 pi. And for one rotation, my change in time is equal to a period, right? So I could write this as 2 pi over period. Or I could say, hey, 2 pi times 1 over period, that's just frequency, right? 1 over period. So I could represent my angular velocity in terms of frequency. And when it's represented this way, this is often called the angular frequency. Okay? Because it's looking at how quickly are we rotating, okay? So that's something that we will see quite a bit when we talk about what are called the equations of motion, that my angular velocity can be represented in terms of my frequency. And then we have a quantity called the amplitude. And so this is the maximum displacement from equilibrium. So in the case of my pendulum, it's like the theta value, the maximum theta value that I pull it up. In the case of my spring system, it'd be like, what's the biggest x value that I pull my spring or compress my spring at, okay? Now, with periodic motion, with simple harmonic motion specifically, it's this repetitive motion. Like you can think of like your spring as kind of like bobbing up and down, right? And so if you were to kind of visualize this, I'm going to try to do this. I don't know how well this will work, but if you could kind of imagine like you're like a vertical spring where you've got this object bouncing up and down periodically, okay? So I'm going to represent that with my marker. I'm going to kind of draw like the position of my marker, and then my board I'm going to represent with time, and I'm, in the sense that I'm going to move my board. So hopefully we kind of get a little snapshot of time, or like little snapshots of time of where my marker is in given point in time, okay? I don't know how else to go, so I'm just going to move my marker up and down. Oh, it worked. So you can see that this up and down movement, this periodic movement, is almost represented as like these like peaks and troughs, and peaks and troughs, and peaks and troughs of like a wave. And this is actually a wave that can be represented as like a sine wave, okay? So these types of position time graphs are sinusoidal in nature. So we could actually represent the position of an oscillator, whether it's oscillating like this, or whether it's a pendulum oscillating like this. That position can be represented with a sine curve. And so we get what are called the equations of motion for simple harmonic motion. You've done equations of motion, right? You've done equations of motion for constant acceleration. You knew that velocity was equal to v naught plus at, that delta y equals v naught t plus 1/2 at squared, and then this one. And then we actually even looked at this in terms of angular quantities when things were rotating around. But I'm going to show you a different way to represent simple harmonic motion in terms of like that oscillatory movement back and forth. And it's represented by a sine curve. So if you were to actually represent the equation of motion for simple harmonic motion, position as a function of time is equal to the amplitude times the cosine of theta, no, lies, of omega times t. Okay? So A, recall, is my amplitude. Omega is my angular frequency. So what this is saying is, at a given point in time, if an object has an angular frequency of omega, I can take the cosine of omega times t, multiply it times the amplitude, and I can figure out where in space, where in position the object is. Okay? But remember, we have another way to represent omega. We can represent omega in terms of frequency, so 2 pi f. So we often see the equation written as the position of a simple harmonic oscillator can be found by taking the amplitude and multiplying it by the cosine of 2 pi f at a given point in time. So this is the equation that's on your equation sheet. Now that kind of looks scary and intimidating. We're not going to go in too much mathematical rigor with this, more so that you need to understand how to identify the equation of motion and what the different parts of the equation of motion mean in terms of this first factor is an amplitude, that you're going to have something times t, and that something is equal to 2 pi times the frequency. You could actually go further and figure out the velocity function with this and the acceleration function with this. If you know calculus, you would just take the derivative of these things. We're not going to worry too much about those. I'll switch to another video that kind of shows you that more pictorially, because I can only draw so well. But you kind of just need to understand this base equation, and then from this equation, you could actually derive the maximum velocity an oscillator will experience and the maximum acceleration an oscillator will experience. So for the maximum velocity that a simple harmonic oscillator will experience, it'll be 2 pi times the frequency times the amplitude. In terms of the maximum acceleration, very similar, but we're just going to square this factor of 2 pi f and multiply it by a. Okay? So this is how you would find the maximum velocity, the maximum acceleration, rather than using kind of these types of formulas for a simple harmonic oscillator. So the video is going to switch, and I'm going to do more of a visual representation of this equation and how it relates to the actual sine graph and cosine graph, and then I'll go through an example problem. Okay, so I wanted to go through a visual example of how simple harmonic motion gives these equations of motions that are sinusoidal. So, but I'm not the best drawer. So here we go. This is a ball and a string, and if the spring by itself would have just this rest length, but when you put this object on there, it pulls down, and this is the equilibrium position with that little ball on it. Now, some external force has to pull it down an additional distance, and then as it's pulled down that distance and let go, it basically bobs back and forth, back and forth, back and forth, back and forth. And if you were to take snapshots of that movement, that's what kind of this visual shows you here, how it's moving down and then up and then down and then up and then down. So that's kind of, if you were to take snapshots of time, in time, you'd see that sinusoidal nature of the movement, right? So that's where we get this equation right here for our position. So remember, for our position, our xt function is equal to a cosine of omega t, but remember that we can use this relationship that omega is just 2 pi times the frequency, and so our equation becomes xt is equal to a cosine 2 pi f times t. Okay. Now, in calculus, you learn that the derivative of the position is over time is just the velocity time function. Okay, and that's just if we think about the rate of the change in position, that's just velocity. So if you were to take the derivative of this function, you would get the velocity curve or the velocity function. And what that one looks like, and I'm not expecting you to memorize this, this would definitely be something that you would be told in a problem, an equation of motion, but the equation for velocity would be equal to negative 2 pi f a times sine, I really didn't leave enough room over here. I'm going to do it over on this side because I don't want to get squishied. So here's my equation for my velocity time. This is 2 pi, oh golly. Sorry guys, I'm really feeling crunched for space here. Okay, here we go. Third time's a term. Vt
is equal to negative 2 pi f times amplitude times the sine of 2 pi f t. Okay, so that is the derivative of this function, and those in calculus should look familiar, right? You take the derivative of cosine, you get negative sine, and you bring in that factor from inside the function. Now, you could also represent this as Vt is equal to negative V max times sine of 2 pi ft, where V max is just 2 pi frequency times the amplitude. So that's how you could figure out what the maximum velocity of your object in simple harmonic motion is. And the maximum velocity occurs at the equilibrium point. Okay, so like right here is where V max occurs. So you could solve that using conservation of energy, but if you know the equation of motion, you could also figure out what the maximum velocity is just knowing the amplitude of motion and the frequency of motion. Okay, and then the rate of change of velocity is just acceleration. So again, if we applied another derivative, so for those in calculus, you should just, if you know how to do this, the derivative of a sine, you know that you're going to get a cosine. For those that are not in calculus, don't worry. You're not expected to memorize these. You're expected to know how to utilize them. So at, the acceleration function, would just be equal to negative 2 pi f quantity squared times a times sine of 2 pi ft. So hopefully you're seeing like what is familiar is like inside. Oh, I got my eraser. What's familiar or is the same as what's inside our function here, this 2 pi ft. Again, you can represent this in terms of a max. You could say that at is equal to negative a max times sine sorry, I always sneeze in twos. 2 pi ft, where a max is going to equal to this 2 pi f quantity squared times a. Okay, so again, I don't expect you to memorize these equations, but I expect you to be able to refer to them, to use them. The one equation that I believe is on your equation sheet, let me check real quickly, is the xt one, the position one. This one is on your equation sheet. Okay. So, and you would know that omega is equal to 2 pi f. So this is the one that is on your sheet, and then you should, if you were exposed to this equation or this equation, and it asks you to reference it in a problem, you should kind of understand where that comes from. Okay. Okay, so let's go through an example of a kind of sinusoidal function or simple harmonic motion, and kind of how you would be expected to utilize these equations. So this says a 2 kilogram object oscillates a total distance of 36 centimeters from a vertical hanging light spring once every 0.65 seconds. So this is very, very similar to this situation, okay? So we're told that it oscillates, it goes back and forth a total distance of 36 centimeters. So that means like going down and then up is 36 centimeters, okay? So keep in mind, it goes down, like if this is equilibrium, it goes down, up, up, down, okay? Like that is one, let me get a highlighter out, that is like one movement of like up and then down and then back. Okay, so that's one oscillation. So if we think about this 36 centimeters, from that I could get that the amplitude of my motion is half of that distance. It is, whew, sorry, my nose is kind of going a little wonky here, 0.18 meters. In terms of my equation of motion, know that my general equation of motion is this. So on your equation sheet, you have this a cosine, it's a 2 pi ft. So you know that's the equation of motion. You know this is your amplitude. You need to figure out what your frequency is. You're told that it goes up and down once every 0.65 seconds. So the period is 0.65. So that means my frequency is just 1 over that. So if I were to plug in these values, y of t would just be equal to 0.18 times the cosine of 2 pi t over, I guess I should have been 0.65. More mindful in my spacing here. Okay, second question, how long will it take to get to the equilibrium position for the first time? So for the first time, notice it does that up and down movement. It takes a total of 0.65 to go all the way through, okay? So to go down and then back up. So if you look at it, the time it's going to take, you can kind of think of it from this graph here. This whole distance, this is that 0.65 seconds. So just to get to the equilibrium position right here would be 1/4 of the period, okay? So it would just be, the time would be 1/4 of my period, which comes out to be 0.1625 seconds. Okay, object's maximum speed. That's where I was showing you that relationship, that the maximum speed is equal to this 2 pi f times the amplitude of motion. So maximum speed is equal to 2 pi f times the amplitude of motion. So 2 pi, my frequency is 1 over 0.65, and then times my amplitude of motion of 0.18. That comes out to be 1.74 meters per second. And then the maximum acceleration, that relationship was looking at that 2 pi f squared times the amplitude. So 2 pi times 1 over 0.65, and that whole quantity is squared, and then I multiply it by my amplitude. And that comes out to be 16.82 meters per second squared. Okay, so if I kind of come back to my visual here, I kind of said this is where my Vmax occurs. This is where my Amax occurs. For a spring, the maximum acceleration occurs when I am stretched the most or compressed the most. So it actually occurs in two positions. Okay, so hopefully that gives you a better visual and understanding of how you would encounter a simple harmonic motion problem.